um, we had tried to talk a little bit about what happens when all the things mix into each other. For example, the two things that we talked about yesterday. Guys. The two things we talked about yesterday were perpendicular bisectors and angle bisectors. One of the things that you guys should notice is that when you have a triangle, how many sides do you always have? 3, which means how many perpendicular bisectors could you have? 3, which means how many angle bisectors can you have? 3. So what happens here is if you try to just draw in a rough idea of where these things would go. What I drew there were 3 perpendicular bisectors. You okay with that? Okay. Excuse me. I'm going to do the same idea with angle bisectors. 3 sides. So then you also could have, like we were saying, you have 3 diagonals. You okay? You step on her foot since she's not worried about it. So again, you get 3 angle bisectors, you have 3 perpendicular bisectors. But here's the weird part. These 2 points, they have names. Okay? When you have 3 or more lines intersect at one spot, it's called a point of concurrency. Yeah. Point of concurrency. I think there's 2 R's in that, but whatever. It's where 3 or more lines intersect. Okay. Now, what happens now is that when you have perpendicular bisectors, and then when you have angle bisectors, this thing called the point of concurrency has its own name. Each one of them has their own name. And on that sheet yesterday, you saw one of them. For the angle bisectors, the point is called the incenter. For the perpendicular bisectors, it's called the circumcenter. So this is for perpendicular bisectors. This is our angle bisectors. The reason why we want to make sure we define both of those terms is because, like you saw on one of those questions you had you guys skip yesterday, where it said point A is the incenter. If you knew that, then there were certain things you could do. Same thing here with the perpendicular bisectors. If you know that it's something that's a circumcenter, there's also certain things we can do with it. And we're going to talk about both those scenarios here in a minute. But what we wanted to do is, first of all, just define them and call them what's called point of concurrency. Okay? So we're going to draw it with all the way out. Obviously, the perpendicular bisectors, you will see right angles, and you will see tick marks, because you have to. Angle bisectors, they'll be a little bit different. They're just going to have, make the dot a little bit bigger, makes it look like the intersect cleaner. you'll have tick marks like this. Okay. Now, now, a lot of times they might not draw all the angle parts, they might not draw all the perpendicular parts, but just the idea of that's where it's going on. So here's what happens. When you have this thing called a circumcenter, I'm going to try and clean this picture up a little bit better. Did not work. we go back to this one, the instructions on that one said that all the perpendicular bisectors meet that all the perpendicular bisectors meet at point G. So if your perpendicular bisectors meet at G, that means this is a right angle, bisected, bisected, right angle, bisected, right angle. So you're going to go with that? So if AD is 20, what's BD? If BE is 15, what's CE? 15. Because we're using the term of a perpendicular bisector. AF is 24, so CF is also 24. Okay? Now you got to look at it carefully. From this point to the vertex is 25, which means this point to the vertex has to be 25, which means from this point to this vertex has to be 25. Because with the angle bisectors, from the point to the vertex is always the same. That's where that comes from. Which do you mean on the lines? Yes, sir. Yep. That's where we're going from point to vertex. Those will always be congruent because it's perpendicular bisectors. It's that circumcenter, when they call it that. Right? Now, it also is asking you to figure out what DG, what GE, and GF were. Well, if you look at it, if I draw it separately, if I say that this is DGA, DGA, this side right here. DA is 20, AG is 25. What do you do to figure out the missing side length in a right triangle? Right there. Something squared plus 20 squared is 25 squared. Doesn't that just become a calculator problem? Okay, take your calculators out and see how we did this. Do I have to square everything right away and then write it down, or can I just do it all at once in the calculator? Do it all at once in the calculator. That's not a big deal. That's why we have them. So in case you forgot where all these buttons were, I realize how slow it takes it. Do you guys all agree that it's going to be 25 squared subtract 20 squared? Just to move that over right away. 25 squared subtract 20 squared and hit enter. Now, you don't have to retype in the 225 to take the square root because it's already stored as an answer. Second, square root of your answer. You guys ever use the answer button? If you haven't used the answer button a lot, get used to using it because when we get to right triangles and we do trig, we use the answer button all the time because it's the last thing stored and you don't have to write it out. Right? And just hit enter. What do you get? There you go. So that means that the missing side length here, DG, is 15. Okay. I go to the next one. Triangle B, G, and E. I move this over. B, oh, no, B was up here, right? Yeah. This guy was the 25. This one was 15. What's that one going to be? just do these same numbers? It'd be 20. Because wasn't the other one was something squared plus 20 squared is 25 squared. Well, that was 15. Well, that means 15 squared plus something squared is 25 squared. What's the something? 20. You don't have to even math that one. So that's your other one. It's 20. You're just using Pythagorean theorem. This is nothing that you guys have to do. And then the last one, it just looks weird because it's a very small triangle. Something, 25, 24. In the calculator, all I have to do is type in 25 squared, subtract 24 squared. What's the square root of 49? If you didn't know that off the top of your head, you just take the square root of your answer. And that's how you get this. Perpendicular bisectors, when you're doing this stuff, as you can see, it's just Pythagorean theorem. Nothing crazy about it. Really not at all. Just understanding that when you have this, from the point to vertex, it's the same. Okay? Point to vertex. On the other hand, though, when we do what's called the in-center, it's from the point to the side. Let's try one of those. I don't have this on a piece of paper for you, so we'll have to kind of look at the diagram and see what we can do. When you look at the diagram, you'll be able to tell right away if you're dealing with angle bisectors or perpendicular bisectors. Because when you look at this one, where are all of the tick marks? The angles. Okay? They're all at the angles. Whereas when you have the perpendicular bisectors, where do all the tick marks wind up? The sides. They both have the right angles because you always measure distance with the right angle. You want to measure square distance. You don't want to measure from here to the wall on a diagonal. Because then your walls won't be straight, won't be square, as they would say it. Stuff like that. So when you're looking at this, you probably don't even need to go through the whole picture. Because if they say that it is an in-center because you're working with angle bisectors, which segments all have to be the same? From the point to the side. So that means that from the point here to the side, these three have to be the same. If you use the vocab, you just write out what you need to do. I know that all three of those are the same, so all I have to do then is, well, if GE 2x minus 7, and GF, x plus 4, what's x? Man, you're very good at mental math. Subtract an x, add a 7. Okay. But did it ask you to solve for x? All right, well, isn't GD going to be the same thing as GE, which is the same thing as GF, if you math it correctly? Okay, so this is real tough now. What's 11 plus 4? 15. I'm proud of you. You didn't even have to take off your shoes. What's 2 times 11? Subtract 7 and you get, hey, look at that, we're on the right track. Is there anything else in here that I can solve for? Are there any side lengths I can solve for? Are there any angles I can solve for? Nope. There's nothing there we can do because I don't know anything else. I don't know any of these other values. I don't know what this guy is. I don't know what this one is. I don't know. That's all you can do. They look a lot more complicated they're going to be. Because if you understand which one you're working with, it's really fast. Remember, in center. The circle is in the center of the triangle. Circumcenter, it goes around it. So it's the shortest, it's the longest. I didn't realize it was that fun. All right. I think so. I don't know. Maybe. Sure. Ish. No.